The peak positions in the NMR give us information about the chemical environment of the process. In other words, they tell us how shielded or de-shielded the chemical proton is, which then allows us to infer whether the proton is attached to electronegative element and how far from its electronegative element the corresponding proton is. In order to be able to quantify these changes, chemists chose a compound to serve as a standard. This compound is known as tetramethylsilane, TMS, and simply a silicon with 4 metal groups. If we think about the electronic structure of this compound, we realize that silicon is an electropositive element, which releases its electron density to metal groups, thus making all the hydrogens very shielded. And so therefore, most of the organic compounds that we encounter will be shielded compared to TMS. And therefore TMS is a convenient substance to be 0 in our scale of NMR peak positions. And so if you look at a typical NMR spectrum, it will start at 0, which is TMS, and it will go through 1, 2, 3, so on, until we hit perhaps 12 or 13, which in most cases is the useful range of proton NMR spectrum. Pretty much all the protons that we'll encounter will come out somewhere in that range. And these numbers are what we call chemical shifts. And we express this with the letter delta. And chemical shift is basically a number which tells us how much more de-shielded our compound is relative to TMS. And so if we were to quantify this, then this would be a difference in absorption frequency compared to TMS. And we have to divide this difference by spectrometer frequency, because if our frequency works on a higher radio wave spectrometer, if our spectrometer works at a higher radio wave frequency, then it will increase this difference proportion. The difference in frequency is very small, and it's expressed typically in hertz, while the spectrometer frequency expressed in megahertz, because it's in radio wave reach. And if we divide these two values, we come out with ppms, parts per million, which are otherwise dimensionless units, showing us that these differences are really very small. But even though they're small, they can clearly be distinguished from each other, so this is a very useful technique nevertheless. Now if we go back to our example of methanol, its NMR spectrum will have two peaks. One will be at 4.8, and this will correspond to the proton of the OH group. The other one will be larger and will be at position 3.4 ppm, and this will correspond to the protons of the methyl group. And very much further down will be the TMS as a standard. Now this chemical shift increases or changes with a variety of factors. So we've seen here that the closer a proton is to the electronegative element, the higher its chemical shift is. If we compare this electronegativity argument in methyl fluoride, where this delta is 4.3, methanol, where it's 3.4, methyl chloride, where it's 3.0, bromide, where it's 2.7, and finally iodide, where it's 2.2, we'll see that the increased electronegativity causes the increase in chemical shift as well. And this electronegativity effect of the neighboring atom depends on the distance as well. And so if we look at the methyl groups in methanol, which observes, as we said, at 3.4, ethanol, where this moves to 1.2, and finally propanol, where this is at 0.9, we will see that the distance from electronegative group, as the distance increases, our chemical shift decreases. And we see that the decrease is quite precipitous because going from methanol to ethanol, we already lose 2.2 ppm units. Finally, the third factor is the third of the easily predictable factors is the number of attached electronegative elements. So if we go from methyl chloride, which is, as we said, at 3.0, to methylene chloride, which is already at 5.3, and then finally to chloroform, which is at 7.2, we see that the number of electronegative elements increases, bringing with it an increase in chemical shift as well. Now, the various classes of organic compounds absorb in various different regions of the NMR spectrum, and these will typically be given to you in a table on exams and quizzes, but it would be good to familiarize with sort of a general range of these regions. And so alkanes typically absorb a very low ppm value. So if we have a methyl group, this will be a 0.9. If we have a CH2 group, a divalent group, this will be about 1.3. And then if we have a methyl, we have a CH group with 3 trivalents, it will be a 1.4. If we go to alkenes, this will be about 5.6 in this region. Or if we have methyl groups attached, this will be 1.7, so much lower. And then finally alkynes, for the terminal proton, which is the only one we can detect, will be with 2.5 and 3.4. Phenyl groups are also very characteristic, so benzene rings will absorb at 7.2 ppm roughly. In other words, on very high ppm values, given that this is just a hydrocarbon. To show the influence of the heteroatom effect, if we have methyl group directly attached to carbonyl, this will be about 2.4. If we have CH2 attached to X, and this X can be either halogen or oxygen, then this will be around 3 to 4 ppm region. If we have an aldehyde, this will be very characteristic chemical shift of about 9.10. So this is a very easy thing to recognize. Carboxylic acids are also characteristic in terms of region, but oftentimes their peaks are so broad that they kind of merge into the baseline, so we can't really see them. And then finally, as we've seen already, if we have an alcohol, these chemical shifts often tend to vary quite a bit, so they're not quite as diagnostic as they could be, because they go from 2 to 5 ppm. So this is the approximate range of these things, which again highlights all the effects that we've shown, that electronegative atoms increase this, and that the closer your thing is to electronegative atoms, the more influence there is. And in the next subtopic, we will see how we can take advantage of the size of peaks in the NMR to determine the number of protons that give rise to them.